Okay, so the next practice problem we're going to look at is sample problem 1316. This problem, we're going to be looking at a baseball that's getting hit by a baseball bat. So here we have a 4-ounce baseball is pitched with a velocity of 80 feet per second. After the ball is hit by the bat, it has a velocity of 120 feet per second in the direction shown. So you'll notice that it's at a 40-degree angle coming off the bat. So it's coming in, pitched at 80 feet per second, and then it's going to hit the bat and it's going to go off at 120 feet per second at that 40-degree angle. If the bat and the ball are in contact for 0.015 seconds, determine the average impulse force exerted on the ball during that impact. Okay, so we are going to kind of get started on this problem, put our knowns and what we're going to find, and then set things up. So this is sample problem 1316. It's on page 865 in your book. We know that the weight of the ball is equal to 4 ounces. All right. Now, so we probably have to have us look it up because we want this in pounds, right? And this is not pounds. So there are 16 ounces in 1 pound. So what we can do is we can do a quick conversion. We know that there is 16 ounces in 1 pound. So the ounces cancel here. 4 divided by 16, that's going to be 0.25 pounds is going to be the weight of that ball. Okay. We know that the velocity of the ball coming in when it's pitched is 80 feet per second, and it's going to the left. Okay, so we're going to have to make sure we identify that on our diagram. And then velocity 2 after it's hit by the baseball bat is going to be going 120 feet per second, and it's going to be going up at a 40-degree angle. Okay. Now, additionally, we know the change in time that force on the bat is going to be in contact with the ball is going to be 0.015 seconds. Okay. And we want to find the average force, okay, of that impulse, okay, the average force. So our approach is going to be the impulse momentum theorem. So if you want to identify that, you can. If you don't, that's okay, but you'll have to identify the equation, which lets me know where you're going. Imp mom. All right, so if we're using that impulse momentum, we know that the mass times velocity 1 plus the summation of the impulse, force times time, is going to be equal to mass times velocity 2. So as we look at our ball, we can kind of show the ball. This is going to be the initial state when the ball is pitched. Okay, that means it's going to the left. Okay, the ball is getting pitched towards the bat, and this is going to be our mass. And I'm going to put of the ball, I'm going to put mass of the ball, B, times the velocity 1. Okay, and again, we know that this is before it hits the bat, so it's going towards it. Plus, okay, this is going to be the impulse. Okay, now this is when the ball is hitting the bat. So the ball is going to experience a force in the x direction times the time that force is going to be on there. Let me make that a little bigger. So this is going to be force in the x direction, Fx times the change in time. So this is the x component of the force that's going to act for the 0.015 seconds. Okay, because it's going up at an angle, it's going to have an x and a y. So there's also going to be an Fy times change in time. Okay, and again, it's the same change in time, but now this is going to be the component so that we can get it up at that 40-degree angle, right? And then here's the center here. And this is going to be the summation of force times the time in that area. And then equal to, And this is the end result of the bat coming off of the ball. I'm sorry, the ball coming off of the bat. This is going to be our mass B times velocity 2. Okay, we know that is 120. The velocity is 120 feet per second at a 40-degree angle. Okay, now because that's at an angle and we deal with horizontals and verticals, we are going to have mass at B times velocity 2x in that direction. And then we're going to have mass of the ball times velocity 2y. A little bit. Mass times the ball, velocity 2y. Okay, so the y component going up. So as you can see here, what we are going to do is we are going to actually look at this to solve for the x component first, so only looking at horizontals, and then we're going to solve for the y components, only looking at the verticals, right? So looking first at the x components. So x components. We are going to assign positive going to the right, okay? So we're going to start off here. It's going to be a negative mass of the ball times velocity 1. As we look at and that's because it's going to the left. So according to our convention, it would be a negative out front, pointing to the left, vector quantity. Our Fx, in this case, when that bat hits the ball, the force on the ball then is going to go to the right. We're going to have a positive Fx times its change in time. So this is the impulse. So this is the initial momentum of the ball, and here's the impulse that it's getting from that bat in the x direction only. We're going to set that equal to now the x of the velocity 2 or the momentum 2. So we're going to have mass times of the ball times velocity 2 x component. Okay. Now, before we fill in down here, let's deal with that x component. We know that this is at a 40-degree angle. Okay, so you guys are statics experts. Our V2x is going to be equal to the cosine of 40 degrees times V2. And we know V2 to be 120. Okay, it's going to be right here. It's going to go down for there. Okay, so let's start filling in our numbers starting on the left-hand side here. So I'm going to have a negative. Now, our mass of our ball, we know that the weight of our ball is 0.25 pounds. The mass then is going to be 0.25 divided by 32.2. Okay. Velocity 1, make sure you carry the negative. I don't want you to forget that. Velocity 1 is our 80 feet per second. So it's just going to be 80. We didn't have to do any converting there. Plus Fx. We don't know what Fx is, so that's just going to stay Fx. And the time that it's in contact is 0.015 seconds. Okay, so it's going to be our unknown. Equal to the mass of the ball. Again, it is going in a positive direction, so don't put a negative in front of it this time. This is going to be, again, 0.25 divided by 32.2 times velocity 2x component. So this is going to be the cosine of 40 times 120, okay? So our V2 was 120 feet per second. That was going up at a 40-degree angle. So that goes there, okay? So our only unknown here is the x component of the force. So go ahead and solve for Fx in this problem. I'm just going to write the final answer instead of all the steps. Maybe I'll write the steps. That way you can compare in case you don't get something to come out. 88.98. Awesome. Thank you, James. Good, good, good. Just want to get another confirmation, make sure everybody's all set to go to the next step. Okay. Awesome. Thank you, Christian. Oh, I put in the time. Oh, it's 0.05. Oh, shoots. Yep. That's going to make a little bit of a difference. 0.015. Yeah. It's easy to, I do it all the time. You know what I do. Okay. So let's start. Got it. Okay. Awesome. Thanks, Josh. So now let's look at our Y direction. Okay. So this is going to be the Y components. Okay. And up is going to be positive this time. Okay. You could put the convention like we normally do in statics up at the top. I just kind of put it here to kind of reiterate, and you'll see the book does that too. So now as we look at the left-hand side, the momentum one, no Y direction anything. So that's going to, if you would, be 0. At the impulse level, we have the Y component times the change in time. Okay, so that's going to be its portion, and then equal to the mass at B, or the mass of the ball, times velocity 2y. Velocity 2y, as you can imagine, is going to be the sine of 40 times V2. Okay, so down here, we are simply going to write this out. So I am going to include the mass B, velocity 1. There's nothing in the Y direction here. This would be 0. Plus Fy times our change in time. It's going to be equal to mass of the ball times velocity 2y. So we would have Fy times 0.015 seconds equal to the mass of the ball is going to be the 0.25 pounds divided by 32.2. And the velocity 2y is going to be the sine of 40 degrees times 120 feet per second. So your unknown here is just your Fy. So your Fy should come out to be, I'll let you guys do that work. All right, you should get 39.92. Excellent, excellent. Yep, awesome. I got 39.9. I stopped mine there. And now because we have the X and the Y directions of this force, as you can imagine, we can use Pythagorean's theorem to solve for the resultant of these two, which would be our average force of our impulse. So that's what we're going to do next. And just want to give you time to make sure you get 39.9. And then we'll go and calculate our force using that Pythagorean's theorem. Okay. Now I am going to draw a little diagram. You're going to notice that for each of these forces, they were positive values. So that means that our X is going to the right, and as we have a picture here, and our Y is going to go up. So I'm going to have my Fy here. Was 39.9 pounds, and then about a little bit more than double. This is going to be my Fx was 88.99. Okay, so that means that I'm going to go here, here. Our resultant force, which is going to be our F, okay? And then we're also going to need an angle, because to fully define a vector, which is this force, we have to also have its direction. So our force is going to be equal to the square root of the Fx squared plus the Fy squared. So that's going to be the square root of 88.99 squared plus 39.9 squared. So your average force should come out to be 97.5 pounds. And then once you have that resultant force or the average force, that is our final answer. We just need the angle that it's at as well. So we're going to calculate for theta. So tan theta is going to be side opposite, which would be our y component divided by our x component. So side opposite is going to be 39.9 pounds divided by 88.99 pounds. Pounds cancel top to bottom, and our theta should come out to be 24.2 degrees from horizontal. And that is the final answer. It's kind of fun. We got to end with, I don't know, feels a little like statics. My favorite. Okay, any questions on this one? Any
Why did
questions?
we plug in 0 for the mass when we were
Oh,
doing the
back
y
here, it
component?
wasn't for the mass, it was because we didn't have a y component here. There's nothing vertical at this level. The mass times
Okay,
velocity. All the velocity of one is all horizontal when it's being pitched towards. So this is when it's being pitched towards the actual bat itself. And not until it hits the bat is when it's going to have that up and to the right, that 40-degree angle. That's why there's this x and y component at the impulse.
okay.
Okay. Yeah. Any other questions? Okay. I'm going to stop the recording here.